Hey guys, so let's finish cellular respiration, and that's the electron transport chain. I won't be drawing here, I will just walking you through the slides in a different way than you can see in your PowerPoint. So let's restep. Well, let's summarize what happened. Remember, focus on the outputs. The output of glycolysis gives you some electron carrier, some more are made in transition step, and some more are made in Krebs cycle. So what happens to all those electrons? We oxidized all those molecules, so we are now ready to actually reduce those electrons into another molecule in the process of which we will harness energy. And remember what I alluded to when I was talking about the electron transport chain in the previous video, and that's really what happens now. The NADH and FADH2 are those oxidized molecules that will actually be reduced by losing electrons, right? And that reduction leads back to the acceptor molecule that's going to be reduced over there. So maybe I misspoke a little bit. The oxidized molecule is just giving its electron. That's over the step of oxidoreduction along the protein transport chain will transport those electrons and reduce a molecule that's going to be, in case of respiration, oxygen. We are not going to details all the oxidoreduction going on here. We're going to talk about what is that energy used for at each of those steps. So remember, we are in the mitochondrion now, and we are at that stage when we can see the outer membrane and the inner membrane with a cristae here that's shown. And everything that I'm going to explain to you, it's one electron transport chain. But keep in mind the mitochondrion has thousands of them along all of those cristae, right? We are focused here on that tiny piece of it. So those electron transport chains are usually made of 4 proteins. There's a transport protein here, and those are fixed, the 3 others. There will be another protein here that's at the end of the step. So what happens? NADH and FADH2 enter at different steps. And that's really all there is to it. It's just that the electron gets unloaded at different protein, which that will explain why FADH2 only yields 3 ATP against 2 instead of 3 here for NADH. So what happens when you unload the electrons? Remember, you shed electrons, you break some bonds, you release energy. That energy came from NADH to NAD plus, NH plus. Not only do you accumulate H plus protons in the matrix, which makes it acidic, because acid, a pH, is the concentration of proton, which is not a good thing, right? Because the matrix is where you have the mitochondrial DNA, you have the ribosomes, you have all the Krebs cycle taking place. But do not fret. Those protons are right away transported across the inner membrane into the intermembrane compartment. That is done thanks to the energy from that release. Why do we need energy for H+? But first of all, H+, although it's really small, it's charged. So it won't go through the membrane easily, right? And the second of all will come when we're done with that step. I will tell you why you need energy to transport those protons across. So the electron now is carrying that transport protein, and that transport protein is also the one accepting the electrons from FADH2. Those electrons are transported to the next protein that will once again use energy from those electrons to transport more H plus into the intermembrane compartment. You see where it's going, we're accumulating H plus is here, so it's coming pretty acidic. That is why that's in between 2 phospholipid bilayers, because that acidic compartment doesn't need to be in contact with the cytoplasm, where all the reaction important to the cell takes place. You don't want to mess up with those enzymes, those protein structures, right, by creating acid. And you don't want to mess up with the Krebs cycle taking place in the matrix of the transition step. So it's all compartmentalized, which is the point of organelles. The last step is that last protein here, the electrons finally shed more energy and more H plus is transported again into the intermembrane compartment. And then the oxygen molecule is reduced into water. So here, I want to emphasize a thing that is really important. What did we see in that respiration? We first breathed out carbon dioxide. Where is that carbon dioxide coming from? The carbon from the glucose that is shed one by one. You're telling me that you are breathing out your sugar. Yes, that's what I'm telling you. You are breathing out your sugar. So I can see you painting now in front of the computer, desperately trying to shed out more carbon and lose some weight, as I've done as myself. It doesn't work because you need to actually exercise. You need to actually use energy. But that's really what it is. When you breathe out your weight. You're not sweating your weight out. When you sweat, you just lose water. You are breathing out your weight. That's why it's so important to breathe openly when you're running. But I hope that that's something that really blew my mind when I learned it the first time. You are breathing out sugar. The carbon that you're breathing out comes from the sugar you're using in glycolysis, in respiration. What is the next thing we learn? The oxygen you breathe in is actually fixed in your body. It's not right away sent back in carbon dioxide. It's actually right away fixed, reduced here into water. So that electron transport chain is when you make your water. You also can drink a lot of it, of course, but you make water here. And what do you do with that water? Remember, glycolysis uses water. Remember, Krebs cycle uses water because you put that water in one of the last steps just before creating FADH too, right? Remember that. So it's used. So now that we realize that we breathe out sugar and create water by breathing in oxygen, which is weird when you think about it this way, now comes the fact of why do you need energy to transport those H pluses? Because you are creating a gradient and you are going against it. Your electron transport chain create that H plus gradient from intermembrane compartment as opposed to the matrix and the cytosol, and that gradient will be used to harness energy. But to create that gradient, you need to go against its gradient by adding protons when there are already a lot. And that's why you need energy to go in active transport. This is not facilitated transport, this is active transport. You use the energy from the electrons. And finally, that's where the magic takes place. Think about that inner membrane as the dam, and think about that ATP synthase as the wind turbine, as the water turbine. Once you open the valve, H plus facilitated transport. This is not an active transport here. This is facilitated transport, a passive form of transport from high concentration to low concentration into the matrix. That just, you open the flow gates and the flood of H pluses goes through, and that ATP synthase harnesses the movement, the energy from the movement, the kinetic energy, to create potential energy via chemosmotic phosphorylation, which is a fancy name for just saying you make ATP out of ADP and phosphate. And that's it. This is how you make energy. And now you know why you use one NADH to make 3 ATP, because you put the NADH releases its electron here, so you can help 1, 2, 3 H pluses going in, and for each H plus going out through the ATP synthase, you make 1 ATP. So NADH yields 3 ATP per NADH molecule, whereas FADH2 does not enter first thing first, it enters later in that protein transport. Therefore, it only allows 2 H pluses to enter the dam, and only 2 H pluses coming from those FADH2 energy, electron energy, will be going out, leading to only 2 ATP being produced by FADH2 molecule entering the electron transport chain. So really think about breathing out your sugar, fixing water thanks to the oxygen you breathe in, the dam of H pluses, and the water of H pluses going through facilitated diffusion, harnessing the energy of a movement from high to low concentration, right? So it's really bringing everything we learned this semester together. Hopefully you can put all those things together in your mind, walk through it. So now we know that the glycolysis helped produce a little bit of ATP, but mostly NADH. That's the most important molecule that is carried along when the pyruvate enters transition step to go and make acetyl-CoA from the Krebs cycle, in the process making more electron carrier. The Krebs cycle, although yielding some ATP, yields a lot of NADH and FADH2. And the beauty of that Krebs cycle is the output is actually used with the input to start over the cycle anew. So you don't need a lot of input for that cycle. And finally, the electron transport chain produce a ton of ATP, 34. So and you need some oxygen. Oxygen is only needed at the electron transport chain, which is the point of the next video when we talk about how can we do respiration without oxygen. We have ways. We'll talk about it. Conversion rates of NADH and FADH2, I just talked about it. 3 ATP for NADH and 2 ATP for FADH2. Revise why in the previous minute I just talked about. But at the end, when you add all those up, 2, 2, and 34, it's 38. And yet the final product is only 36 because and it's theoretical, it's when everything works perfectly, right? Which is never the case. But it's used, 2 ATP are used to transport those NADH and FADH to the electron transport chain. You didn't think it was a freebie. You need to transport those things. And that transport costs some energy. And so you use some of those ATP. So at the end of the day, it's 36. It's theoretical. But if you learn your outputs, net output 2, 2, and 34, you get the 38. And you just have to remember that 2 are used for a transport. And it's 36. And if you had it, that's your electron transport chain. Okay, I'll see you guys in the next video when we finish respiration by talking about the anaerobic respiration and some of other ways we can do glycolysis. Okay, you guys take care. Bye-bye.